In the realm of protective relaying, the term cold load describes the characteristics of the electrical load connected to a system when that system is in a de-energized state. Understanding cold load is critical for ensuring the proper operation of protective relays and the overall reliability of the electrical grid. A cold load is primarily composed of non-inductive elements. Think of devices like lighting fixtures using incandescent or LED bulbs, electric heating elements found in space heaters or ovens, and other resistive components that draw current directly proportional to the applied voltage. When a power outage occurs and the system is subsequently re-energized, a unique phenomenon arises. The initially non-inductive cold load exhibits a surge in current demand that can be significantly higher than the normal operating current. This inrush current is due to several factors. Firstly, many resistive heating elements have a positive temperature coefficient. This means that their resistance increases as they heat up. When cold, their resistance is lower, resulting in a higher initial current draw. Secondly, lighting loads, especially older incandescent bulbs, draw a substantial inrush current as the filament heats up from a cold state. Thirdly, any electronic devices with capacitive input filters will also exhibit a current surge as the capacitors charge up. This high inrush current can create challenges for protective relays. Protective relays are designed to detect abnormal conditions such as overcurrents, short circuits, and ground faults, and to quickly isolate the affected section of the system to prevent further damage and maintain stability. These relays typically have settings based on the expected load characteristics under normal operating conditions, which often assume a predominantly inductive load profile. However, the presence of a significant cold load can cause the relay to misinterpret the inrush current as a fault, leading to a false trip. A false trip occurs when a protective relay operates unnecessarily, interrupting power supply even though no actual fault exists. This can disrupt service to customers, cause inconvenience, and potentially damage equipment. Therefore, it is essential to account for the effects of cold load when setting protective relays. Several strategies can be employed to mitigate the risk of false tripping due to cold load inrush. One approach involves implementing time delay settings on the overcurrent relays. This allows the relay to ride through the initial inrush current surge without tripping, while still providing protection against sustained overcurrents. The time delay should be carefully selected to be long enough to accommodate the expected cold load inrush duration, but short enough to provide adequate protection against genuine faults. Another technique involves using relays with harmonic restraint or blocking features. Cold load inrush currents typically contain significant harmonic components, particularly second and third harmonics. Harmonic restraint or blocking functions can prevent the relay from operating during periods of high harmonic content, thus improving its immunity to cold load inrush. Some advanced relays offer adaptive settings that automatically adjust the relay's sensitivity based on the system's operating conditions. These relays can detect the presence of a cold load condition and temporarily modify their settings to prevent false tripping. Adaptive settings can be particularly useful in distribution systems where load characteristics may vary significantly depending on the time of day or season. Furthermore, it is crucial to perform thorough testing of protective relays under simulated cold load conditions. This involves using relay testing equipment to inject realistic cold load inrush currents into the relay and verifying that it does not trip unnecessarily. Relay testing should be performed during commissioning, after any modifications to the system, and periodically as part of a regular maintenance program. When selecting protective relays for applications where cold load is a concern, it is important to consider the relay's cold load pickup characteristics. Cold load pickup refers to the relay's ability to withstand cold load inrush currents without tripping. Relays with high cold load pickup capabilities are generally more suitable for such applications. The cold load phenomenon is not limited to residential and commercial distribution systems. It can also occur in industrial facilities, particularly those with large motor loads. When a plant experiences a power outage, many motors may stall and draw high inrush currents upon re-energization. This can create a similar cold load effect, potentially causing protective relays to trip and disrupt the plant's operations. In industrial settings, it is often necessary to coordinate the protective relays to account for the motor starting currents. This involves setting the relays to allow for the motor's starting time without tripping, while still providing adequate protection against motor faults. Motor overload relays are specifically designed to protect motors from overheating due to sustained overcurrents. These relays typically have inverse time characteristics, meaning that they trip faster for higher overcurrents. Motor overload relays should be properly coordinated with the upstream protective relays to ensure that the motor is protected without causing nuisance tripping of the entire system. In addition to protective relays, other devices can be used to mitigate the effects of cold load inrush. For example, soft starters and variable frequency drives can be used to limit the inrush current drawn by motors during starting. These devices gradually ramp up the voltage and frequency applied to the motor, reducing the magnitude of the inrush current. Surge suppressors can be used to protect sensitive electronic equipment from voltage spikes caused by cold load inrush. Surge suppressors divert excess voltage to ground, preventing it from damaging the equipment. Understanding the composition of the cold load is crucial for selecting appropriate mitigation strategies. This requires analyzing the types of load connected to the system, their individual inrush current characteristics, and their contribution to the overall cold load demand. Load studies and power system modeling can be used to simulate cold load conditions and predict the behavior of the system during re-energization. The results of these studies can be used to optimize relay settings and select appropriate mitigation devices. In some cases, it may be necessary to implement load shedding schemes to reduce the impact of cold load inrush. Load shedding involves selectively disconnecting non-critical loads during re-energization to reduce the overall demand in the system. This can prevent the system from overloading and improve its stability. Load shedding schemes can be implemented manually or automatically using programmable logic controllers or other control systems. The specific design of the load shedding scheme will depend on the particular characteristics of the system and the priorities of the operator. The NEC, or National Electrical Code, provides guidelines for the protection of electrical systems and equipment. While the NEC does not specifically address cold load, it does contain requirements for overcurrent protection, coordination of protective devices, and motor protection. These requirements are relevant to the mitigation of cold load effects. For example, NEC Section 430.52 specifies the maximum allowable overcurrent protection for motor circuits. This section provides guidance on selecting appropriate fuses or circuit breakers to protect motors from short circuits and ground faults while still allowing for the motor starting current. NEC Section 240.12 addresses coordination of overcurrent protection. This section requires that overcurrent devices be selected and coordinated to minimize the extent of an outage caused by a fault. This means that the overcurrent devices closest to the fault should trip first, while upstream devices should only trip if the fault is not cleared by the downstream devices. Effective coordination of overcurrent devices is essential for mitigating the impact of cold load inrush. Furthermore, NEC Article 700 addresses emergency systems, which are often used to provide backup power to critical loads during power outages. Emergency systems must be designed to operate reliably under cold load conditions. This may require the use of special transfer switches that can handle high inrush currents, or the implementation of load shedding schemes to reduce the demand on the emergency generator. In summary, cold load is a significant consideration in the design and operation of electrical systems. Understanding the characteristics of cold load, its impact on protective relays, and the available mitigation strategies is essential for ensuring the reliability and safety of the electrical grid. By implementing appropriate relay settings, using advanced relay features, performing thorough testing, and employing other mitigation devices, it is possible to minimize the risk of false tripping due to cold load inrush and maintain a stable and resilient power system. Firstly, cold load refers to the load connected to an electrical system when the system is de-energized. Secondly, this load primarily consists of non-inductive elements such as lighting, heating, and other resistive devices. Thirdly, upon energization, the cold load becomes an inductive load due to the presence of motors, transformers, and other inductive devices. Fourthly, this change in load characteristics can affect the operation of protective relays. Fifthly, protective relays typically have settings based on the assumption that the load is inductive. Sixthly, when the load is predominantly cold, these settings may not be appropriate. Seventhly, this can lead to false tripping or incorrect relay operation. Eighthly, it is important to consider the effects of cold load when setting and testing protective relays. Ninthly, relay testing equipment can simulate different load conditions, including cold load. Tenthly, understanding and addressing cold load is crucial for ensuring the reliable and safe operation of electrical systems. Let's further explore the practical implications of cold load in various electrical systems. Consider a residential neighborhood that experiences a power outage during a cold winter night. Most homes have electric heating systems and lighting, which constitute a significant cold load. When power is restored, the heating elements and lights all attempt to draw current simultaneously, resulting in a large inrush current. This inrush current can overload the distribution transformer serving the neighborhood, potentially causing it to overheat and fail. It can also cause voltage dips that affect other customers connected to the same transformer. To mitigate this, the utility company may implement a staggered re-energization process. This involves gradually restoring power to different sections of the neighborhood, allowing the system to recover before energizing the next section. This reduces the overall inrush current and prevents overloading the transformer. In commercial buildings, cold load can be even more pronounced due to the presence of a variety of equipment, including lighting, heating, ventilation, air conditioning, computers, and other electronic devices. When power is restored after an outage, all of these devices can contribute to a significant inrush current. This can trip circuit breakers, damage equipment, and disrupt business operations. To address this, commercial buildings often have emergency generators that provide backup power to critical loads during outages. The emergency generator must be sized to handle the cold load demand, and the transfer switch must be able to handle the inrush current without failing. Furthermore, commercial buildings may employ power management systems that can shed non-critical loads during re-energization to reduce the overall demand on the system. In industrial facilities, cold load can be particularly challenging due to the presence of large motor loads. When a plant experiences a power outage, many motors may stall and draw high inrush currents upon re-energization. This can cause protective relays to trip, disrupt production, and potentially damage equipment. To mitigate this, industrial facilities often use soft starters or variable frequency drives to limit the inrush current drawn by motors during starting. They also coordinate protective relays to allow for motor starting currents without causing nuisance tripping. In addition to the examples above, cold load can also be a concern in other types of electrical systems such as data centers, hospitals, and transportation systems. In data centers, cold load can affect the performance and reliability of critical servers and networking equipment. In hospitals, cold load can disrupt patient care and endanger lives. In transportation systems, cold load can cause delays and disruptions to service. Therefore, it is important to consider the effects of cold load in all types of electrical systems and to implement appropriate mitigation strategies to ensure reliable and safe operation. Understanding the specific characteristics of the electrical system, the types of loads connected, and the potential consequences of cold load is essential for developing effective mitigation plans. This requires a collaborative effort between electrical engineers, facility managers, and utility companies. By working together, we can ensure that our electrical systems are resilient and able to withstand the challenges posed by cold load. In addition to the technical aspects of cold load, it is also important to consider the economic and social implications. Power outages caused by cold load can result in significant economic losses due to lost productivity, damaged equipment, and spoiled goods. They can also cause inconvenience and hardship for consumers, particularly during extreme weather conditions. Therefore, investing in cold load mitigation measures is not only good engineering practice, but also a sound economic and social policy. By reducing the frequency and duration of power outages, we can improve the quality of life for consumers, enhance the competitiveness of businesses, and strengthen the resilience of our communities. In conclusion, cold load is a complex phenomenon that requires careful consideration in the design and operation of electrical systems. By understanding the causes and effects of cold load, and by implementing appropriate mitigation strategies, we can ensure the reliable and safe operation of our electrical grid and protect our communities from the consequences of power outages. One should never disregard the profound impacts of power restoration following extended outages, which can easily trigger unforeseen cascading effects. Therefore, a proper grasp of cold load dynamics, as it concerns system protection and relaying, is thus indispensable for any power engineer or technician working to secure a robust and reliable electrical infrastructure.